Good day, ladies and gentlemen. You're all very welcome to this week's CNPS Saturday technical session, hosted by me, Ian Cowan. Now, today we have the second of a three-part series on the STOE, which is the Scalar Theory of Everything, developed by John Hodge. Now, John has these three videos, which he has given us permission to show and comment on. Actually, John is present, which I'm delighted to be able to report. He was here the last time as well, and we're hoping he'll be here next time. But he asked us to show these videos, which are pre-recorded and they're more rehearsed. And I think he was happier that we use those as a basis for our subsequent conversation. So, as usual, we'll have a number of people in the green room who will be able to address points in maybe some detail and get into some fairly protracted conversation with John, indeed, because John is here to answer the questions. I think we'd be a bit pushed to guess all the answers, if he were not here. There will, in addition, be people participating through the Facebook and YouTube videos, media systems. I see nobody is actually in yet, but they will be in shortly, I'm sure. And we'll deal with their questions insofar as we can. So let me see. I'll just read out again, just in case you haven't seen the announcement. Today we're talking about the Scalar Theory of Everything, and in particular, it's part 2 of a 3-part session: Pioneer, Anomaly, and Planet 9. And we've described it in this way, which I hope is not too inaccurate. John can tell us later if so. Applying the Scalar Theory of Everything on a solar system scale explains a concerning anomaly regarding unpredicted accelerations of the Pioneer spacecrafts, the 2 spacecrafts, and also the irregular orbits of trans-Neptunian objects, which have been hypothesized as due to a 9th planet. So we'll see what that is. Okay. So what I did last time is I started by sharing my screen and then brought the video up, making sure I had the audio. So let me. I'll actually just bring John up for the moment while I'm doing that, in case there's any suggestions. So let's see, present. I think the best way is to share my screen and then get the video up. Let me see now. Entire screen, yes. Now, share. Now, all I have to do is get the video up, and I have this somewhere here. Here it is, actually. I dare say you can hear the audio and so on. So what I'll do is I'll maximize that. It lasts for just under an hour, and I'll play it.
So now let's address the B-band luminosity issue that I talked about before. Here is a sample of the...
I'm just stopping that for a minute because I want to double check that everybody can hear everything. I'll check with John as usual. So, John, could we hear that? All right.
I could, yes.
Okay, well then if you can, I'm sure everybody else can. So I'll go back. Thank you. Let me see now.
Data. This one in particular is looking at the asymmetry of rotation curves. There's the paper where you can see this. You'll note that what I do is I look for data that exists and I plot all the galaxies that I find. Now, each of these points is basically a luminosity parameter versus the asymmetry as noted. And you can see the data points. I've drawn lines through several. You notice these are grouped as on one line. These then come as another line. The difference between these lines is approximately, the difference between the slopes of these lines is approximately 2. And that, I think, is very significant. Now, competing people, that is to say the standard practice in the industry, will take a look at a graph like this, and they'll plot some line that comes someplace like that. Okay? Many in the physics community will take a look at this kind of data. They'll plot a line going someplace out like that. And they accept then a large error. This is approximately 30% error. Accept a large error. And when they take a look at these kind of things, they will say, whoops, there's something wrong with these galaxies. Therefore, they will select these galaxies out of their sample. And then they accept only these galaxies in their sample. And that's roughly 80% of the galaxies. Well, 80% is pretty good, and most of them go along with this. I don't do that. I'm looking at all the data, and all the data is going to include these very funny galaxies that seem to be standalone galaxies. And we note that the relationship between this one and these down here. So what I'm detecting here is a very interesting, to me anyway, in that between these lines is a gap. The galaxies don't appear in here. You see, there's nothing here. If it was evenly distributed, or say randomly distributed, you would expect to see some galaxies in where we have gaps. So why do we have these lines whose slope differs by about a factor of 2? That becomes a problem to be solved. But having different types of galaxies is not unusual in the universe. Here we see what is known as a Hubble classification scheme, where you got elliptical galaxies, and then spiral galaxies, all out here. Some of the spirals have bars, and that's these things, where you note that that's the bar, that's the B here, and others don't. Now it's kind of interesting that there are 6 of them and 6 of my lines, but I looked for a correlation here between this morphology type and my lines and didn't find it. But there have been some interesting things that come up, which we'll get into later on. Rotation curves. The discrepancy between the Newtonian and general relativity mass and star and gas kinematics in spiral galaxies is well established, and they're called rotation curves. There are some issues here which I'd like to address. The focus has been on flat rotation curves. And the outer part of some spiral galaxies. But rising and falling rotation curves also exist, and these things are falsifiers of dark matter, falsifiers of the modified gravity, and the MOND. Now, the general rotation curve is generally not understood, but in general, close to the center of spiral galaxies, the rotation of stars and all is up into the thousands of kilometers a second. Okay, this is the data of the S stars in our galaxy, thousands of kilometers a second. And this is all within, the center of the galaxy being within 12 AU of Sagittarius star position. But the other thing you realize is the decline from that thousands as you go out in terms of AU is very rapid, and it's Keplerian, meaning it obeys Newton's law. But then a funny thing happens. Someplace very close to the center in the bulge, the rotation velocity becomes very, very low. Some say even zero. That is to say, it's as if there is no mass effect beyond this point outward. It's zero. But that's not what we see. So here you have some matter beyond this 0 point, and the rotation velocity is increasing. But can't be due to any mass here in the middle, because this is zero. This then is a problem. Ouch. Ouch. Ooh. The problem is termed as why are outer galaxy parameters, meaning parameters out here, related to inner galaxy parameters, like the mass of the central massive object and if this creates a problem. The problem is, it has been noted that outer galaxy parameters out here are related to inner galaxy parameters such as the mass in the central area of the galaxy. But with this being very close to zero here, that relation should not exist in normal Newtonian or general relativistic equations. Now, that means there's mass accumulating here at this point, and it's increasing, and this then is due to the mass here. What happens out here is due to the mass in this zone, and not to anything in the central area of the galaxy. And as you can point, as I diagrammed here, the rotation curve can be more or less flat, which most galaxies are. There's a significant portion of them, that have a rising rotation curve, and very limited, I might add, and some that are actually falling. Just as a note, rotation curves usually measured along the major axis from our viewpoint. Stars near the center have rotation velocity that's very high. Here's an example of 4321, and this is the paper you see it is. And here we plot rotation velocity versus the distance from the center, and we've kind of ignored the very center. This is from the zero line. here for the filled diamonds, which is HI, and the filled diamonds extend out beyond the luminous range. And you see it's anything but smooth going out. But anyway. Here's the same galaxy, same plot, only now we're looking at H alpha line. And the H alpha line is essentially ionized hydrogen. That means these are luminous stars you may see, whereas beyond this zone here, this is molecular hydrogen, and you generally don't see it, it just goes on. And this is the zone that is considered the flat zone out in here. In here is the rising zone, and you see the rising is anything but uniform. Asymmetry. This is kind of busy, but you have to do something. This comes from this paper, and we have a little problem of just exactly what do you mean by asymmetry. What the STOE does, here's one side of the galaxy and the other side from the center, and you'll notice that the two have a slightly different rotation difference in the rotation curve. That is the STOE asymmetry. Now, other people don't look at this as being asymmetric. They draw it simply as one line, therefore they ignore the asymmetry. But the truth is that most galaxies have some amount of asymmetry as measured like that. For 20 or 30 years, there were papers being published about asymmetry, and nobody come up with a good model for what asymmetry was or how it was caused, and therefore they just seem to have stopped looking. Well, asymmetry is part of the data, and we do have to look at it. The evidence suggests that cluster environment affects the RC is contradictory. The evidence that cluster environment affects the rotation curve is somewhat contradictory. This is because it typically follows the ionized hydrogen rather than the outer galaxy molecular gas. Ionized hydrogen being stars, and stars kind of stop about halfway out of most galaxies, most spiral galaxies. And the molecular hydrogen then becomes much more sensitive to environmental effects than our stars that are fairly far inside galaxies. Also, in the STOE, asymmetries in other people's, also asymmetries in the side-to-side variation in the outer parts are nearly all galaxies, but are usually ignored. They are averaged. Many characteristics of RCs are unexplained. Many falsify current models, including infall models required by the Big Bang model. Others have rising rotation curves from the minimum outward, implies a slowly increasing amount of mass from near zero is affecting the RC. That is, as if there is no mass effect of the central region around supermassive object in the center of the galaxy. Why is the disk centered around the supermassive black hole when the calculations show no mass effect of the supermassive black hole on the disk? Or what is the relation of the central mass to the disk parameters where no relation should exist? other discrepancies with the accepted model. This is an example here where this doesn't look like a nice rounded smooth, right? It has very sharp delineation points, such as right there and right there. You see, so it looks like a piecewise linear fit to this data is a better fit than some kind of a nice smooth curve. So the STOE has three forces acting on matter outside of the center region. One is the gravity of the inward mass. Now this is not the bulge mass near the central mass of black hole. This is the mass outward from where the rotation curve reaches a minimum near zero. The effect of the source strength is still there because the plenum is still acting. Therefore, it's ejecting, which is what the negative sign here is all about. Plus an effect from nearby galaxies. In the STOE analysis, we take a look at the difference in rotation velocity at some distance along the major axis. This is a degree definition of what asymmetry means. Most people take asymmetry to be difference of radius to get to a given rotation velocity. So this is unique to the STOE. My sample, when I did the work, was 105 spiral galaxies, which is all for which RCs were found. There was no selection bias here. If it had an RC published, I went with it. 16 of these galaxies had Cepheid-Star distance calculation, which we consider very, very accurate. 49 of the sample had published asymmetric RCs. Many others probably had it, but I couldn't find the data. Here then are the 16 that have the good distance, the Cepheid distances relations. You'll notice this one, this one, and this one all have rising rotation curves. These things are falsifiers of dark matter. Some others have some unique structure, like here, in the outer part of the rotation curve, which is, again, molecular hydrogen, not stars. And these are then very sensitive to what other galaxies are doing. Note the uncertainty here. Remember I wrote my little lecture about doing the data. These are the equations. There's a B band luminosity. This B is going to be approximately 2 for these kinds of equations. And you'll note that if you don't take account of the asymmetry, you end up with something around 10 to 20% uncertainty. Okay. But that's still good, because when you take effect of all those so-called outliers, if you just want to form one line rather than this many factors, you end up with 30% uncertainty and having many galaxies ignored. However, when you do the same thing and you include the asymmetry in the RCs, and here we're looking at these things with the asymmetry, this is the asymmetry, involved. There's the effect of the neighboring galaxy, and you notice that suddenly these uncertainties really decline. So there's no reason why you should have very high inaccuracies, except for selection bias and because asymmetry being improperly accounted for. Okay, so here's the issue of the inner rotation curve dropping down to zero in a purely Keplerian fashion. The galaxy's central mass and central velocity dispersion are the two measures, and B-band luminosity correlation in the outer galaxy. Many researchers have noted this correlation, but is generally unexplained in the standard model. The STOE suggests the amount of matter and therefore structures derived from source and sink strength and not from the direct attraction of the central mass. And here's the central velocity dispersion, and we got a nice relationship going here. This is the central mass. A prediction. Here what we're doing, back in 2003, 2005, we were suggesting that neighboring galaxies influence rotation curves. There's the paper. Generally, this has been ignored throughout the years. However, starting in around 2017, some papers began to suggest that the correlation of spiral galaxies tilt related to neighbor galaxies. Well, this is kind of a prediction, meaning the STOE has always suggested that neighbor galaxies do influence other galaxies. So, the STOE model is an alternative to and is more complete than relativity, the Big Bang model, and the QSSC model. It is Machian. It explains many problem observations and includes the small in the first video. The unexplained blue shift in the radio signal from the Pioneer spacecraft is well established. The Pioneer anomaly is experimentally observed as the residue of a frequency shift after the Doppler shift effect is subtracted by expressed as an apparent acceleration. This is based on a notion that the Doppler shift applies to the residue. This assumption is unsupported. Another unsupported assumption is that the blue shift is sun-directed. Pioneer anomaly could be an effect other than a real acceleration, such as a time acceleration or an effect of an unmodeled effect on the radio signals. Although unlikely, a currently unknown systematics effect is not entirely ruled out. An obstacle to a new gravitational physics explanation of the Pioneer anomaly is that a modification of gravity large enough to explain the Pioneer anomaly is in contradiction to the planetary ephemeris unless the equivalence principle is violated. The accepted opinion is that cosmic dynamics, according to general relativity, has far too little influence in galaxies to be measurable, and that the expansion of the universe is essentially negligible for scales up to galactic clusters. Further, the expansion of the universe indicated by redshift has a sign opposite to the acceleration. Data for the existence of the acceleration from Galileo, Ulysses, Voyager, and Cassini spacecraft are suggestive, but inconclusive. The currently accepted explanation is that thermal radiation from the spacecraft exerts a sunward recoil force. The problem, there are several other characteristics of the data that are ignored. The Scalar Theory of Everything model for the Pioneer anomaly is that matter causes a static warp in the plenum that causes the effect on the signal. The gravitational attraction, the equivalence principle, and the planetary ephemeris remain as described in general relativity. Therefore, the equation used to calculate the redshift for galaxies applies, where the matter acts like sinks in the equation and the observed blue shift is the negative of the galaxy redshift. You can see my video about redshift. The amount of warp, rho, at a point in space was posited to be equal to the gravitational constant times the mass of a body divided by the distance to the point. And to get rho at a given point, you sum over all masses. The equation for the calculated redshift is as in the galaxy redshift. The terms are defined in the redshift video except for dl is twice the distance, and two of the terms are zero because the distance we're concerned about here is small relative to galaxy distances. This is the data for Pioneer 10. The diamonds are the data, which are here, here, and here. The squares are calculated, and you see it's a pretty good fit. The X's here are calculated for dates 10 days from the date of the data, and that's because the duration of taking a data point has been about 10 days. This is for the Pioneer 11 spacecraft. This point here is the Saturn encounter, and you'll note that before the Saturn encounter, there looked like there could have been a redshift here, but a very slight blue shift at least. Then the Saturn encounter had a very large error associated with it, and these are two things that are unexplained by the current model. Because the value of the acceleration depends on the closeness of matter to the line of sight, a change over 10 days or longer is due to long integration times. The correlation coefficient we saw in these two previous graphs is about 0.93. The following are the other observations of the Pioneer anomaly that are poorly explained by other models. First is the annual periodicity. Anderson noted an annual sinusoidal variation in residue of the data. Sinusoidal means a circular motion around some point at a constant radius. Such a motion is the apparent motion of the sun around the Earth. There is a sine term, is the distance of the sun to the line of sight. Line of sight to the spacecraft, the angle we're concerned about is sun, Earth, spacecraft, and this is then the sine of that angle. If the angle, sun, is large, in this case where the sun is on the other side of the Earth from the spacecraft, then we get a nice, smooth, 1/r kind of distribution. If the angle to the sun is small, then we have the effect of the sun on the electromagnetic signal. You will note this is similar to the discrete redshift. The same applies to the sidereal periodic motion. That is to say, the send and receive station of the signal is on the surface of the Earth, and there's a constant radius between the center of the Earth and the radio station. The difference in the acceleration between spacecraft is because the outer planets are on the opposite side of the sun, or P10. The effect of the planets on the acceleration of P10 is less than on P11. However, as d of the P11 increases, the planet's effect approaches a constant value. The STOE expects the galaxy mass to have a small difference between the spacecraft caused by their different travel directions. The orbit of P10 is closer to the Sun's Sagittarius A axis than P11, and the distance of P10 is greater than the distance of P11 because it's been in space longer. Now, the Sagittarius A is where we think the source in our galaxy is located. However, the effect here is within uncertainty levels. The difference between the two programs' methods for analyzing data are different in the early stages of the Pioneer 10 and closer in agreement at the later stages of the Pioneer 10. The varying acceleration may explain the difference. The AP is not constant, as one of the programs assumed. The slow decline in the acceleration, the radio signal measurements are from the and to the Earth. At small distance, the relative effect of the Sun-Earth distance is larger than at farther distance. As d increases, the solar system effect appears to approach a single mass located at the very center of the solar system. Therefore, the acceleration declines and approaches a constant value dictated by the rho being inversely proportional to the negative of the distance. However, the STOE expects that at much greater distance, the effect of the galaxy mass will increase to cause a difference in the AP values between the spacecraft. This plot shows the acceleration varies widely over a period of hours closest approach of P11 to Saturn. The negative acceleration calculation is a redshift, as seen in the previous figure. Data at the beginning of the encounter has a near-zero blue shift. A large uncertainty in the second P11 data point is the Saturn encounter. This data point extends over a relatively long time, some 50 days. The rapidly varying acceleration in the previous slide is consistent with the uncertainty. You'll notice the angle of the Sun is nearly on the other side of the Earth from the spacecraft, and so it doesn't play much of a role. The cosmological connection. Here's a plot that we had in the redshift video, where we have distance versus the X factor, and we see something very similar to what we saw in the redshift video, except that the sign is different. There's the formula for the graph like we did before. This has a 95% correlation coefficient, and we calculate H0 to be 106. The Pioneer anomaly and the redshift of cosmology are the result of the same rho effect on light. In the cosmological redshift calculation, the Z follows the Hubble law if rho is inversely proportional to the radius. In the gravity well, the redshift follows a negative Hubble law. That is, rho is inversely proportional to the negative of the radius. Hence, the negative of the galaxy redshift cosmological constant. Galaxy redshift and discrete redshift are the same phenomena as the Pioneer anomaly. Predictions of the STOE in 2006 concerning the Pioneer anomaly that no other model predicted have been published later in 2009 and 2011, and these are the two papers it was published in. Because the Pioneer 11 data before the Saturn encounter was near zero, the accepted explanation was there was no Pioneer anomaly before Saturn. The data before the flyby encounters were insufficient to detect the Pioneer anomaly. That's what the paper showed. It still requires that to be the case, rather than that there was no Pioneer anomaly before the Saturn encounter. The Earth direction is marginally preferred. Other models, including the thermal recoil model, consider the Pioneer anomaly to be sun-directed. Earth-directed implies a signal effect, which is what the STOE has. We quote, the data favor a temporarily decaying anomalous acceleration. The decline is exponential according to the STOE, except when the signal passes near a large mass, such as during flyby maneuvers. The STOE model, all the data of the Pioneer anomaly is not just the one type of data. The STOE model has made predictions that have been discovered later. The STOE model is more universal because the physics is the same as for galaxy redshift. Now that the transparent mass project and the special relativity project are done, except for writing the papers, it's time to consider what's next in the STOE. This paper will show you about where we are, and many of the projects we've had in the past have threads which could lead to more interesting stuff, and those are all possible projects for what's next. The STOE is causative and Machian model. It reduces to general relativity and quantum mechanics, which makes it a theory of everything, and explains many problematic observations that both general relativity and quantum mechanics have. It has made predictions, which have later been found to be true. The STOE rejects, by experiment, Maxwell's equations, wave models of light, and the idea of the Lagrangian and the Hamiltonian mechanics, which do not have dissipative characteristics. One thing we can look at is the constants of the universe. As a result of negative feedback loops. The problem here is identifying what the feedback loop is. This was done for the cosmic microwave background temperature, which is a typical temperature feedback loop in that paper. Looking at the gravitational constant is another thing we can look at. The STOE uses three types of mass, which comes from Newtonian physics. The weight, which in the STOE is a plenum gradient onto the surface area of a Hodge. The inertial mass, which is in the plenum, so it supports wave actions. And the gravitational mass, which is what Hodge caused in the plenum wave. This works well for photon simulation, which was done. So gravitational constant changes with body structure and perhaps with plenum level. The strong equivalence principle here is rejected, but the weak one is accepted. Entropy and the arrow of time is another thing I've been thinking about for quite a while, and it's still quite a problem. It occupies about a foot-high paper on my desk that I should look at. Universe entropy must include a dissipative or friction term. The standard models are Lagrangian and Hamiltonian, which do not. Therefore, the current universe model of entropy is not accepted. Causality of changing events implies energy input or output. If output, then the arrow of time from source to sink, as you see in the galaxy structure, suggests a constant universe entropy, rather than entropy is always increasing, as this current model suggests. We could also apply the redshift equation to the Pound-Rieck experiment. Z has already been applied to the Pioneer anomaly, all 10 of the anomalies, whereas the standard model only applies to one of the anomalies, which means it's not that good of a model. This model made predictions which were later confirmed to be true. We could apply the photon simulation to reflection, refraction, and the quantum eraser experiments. This has several problems associated with it, but maybe what we could do is redo with the length of the plenum wave as a function of the number of Hodge in the photon, rather than using the model of linear dipole antennas. Now, Bohms has suggested a point particle, and the STOE doesn't accept point particles, it accepts some extended space. And we could do this rather than indirectly, as the photon simulation currently suggests, as a body with volume rather than a point. I would note something of interest here, and that is these Walker experiments, which use only one drop to make waves, which then cause diffraction when going through a slit. This is why we might look at the length of the Plenum wave concerning with the mass of the photons. It may be easier with this to consider reflection. We could apply the rotation curve equation to spiral galaxy orientations. Recently, some papers over the last 5 years or so have noted correlation of spiral galaxy disk orientation in space being somewhat related to their neighbor's position. Now, the asymmetry of the rotation curve was considered, and it considered these neighbor galaxies, and so this spiral galaxy rotation orientation may be considered a prediction of the standard scalar model. This is the issue that we have. Currently, where here you have rotation velocity squared compared to all these galaxies and versus B-band luminosity. Now, you'll note that there seems to be several relations. The slope of each of these lines is twice the previous line. And this area in between the lines is actually a void area. Now, the slope of the lines differ by approximately 2, and statistically, the form is significant by rejection of the null hypothesis that the data points are random. What galaxy characteristic does the B-band luminosity depend? That's the problem. If we could find that, maybe we could have just one nice line in the previous graph. That would also apply for central mass, which was another paper. Another effect of the source at the center of Milky Way we could look for. We've already applied it to RCs, as we said. Planet 9 is a paper, there's 2 papers on that. Mercury and other planet orbits seem to have some relation to the source in our Milky Way. And of course, the source in our Milky Way was part of the Pioneer Anomaly paper. We could expand the idea of structure of particles being like disk magnets to quarks. What that structure appears to be that it's going to be like electrons being held together by photons is what it looks like. But, I've yet to come up with a structure. I could form a ball of disk magnets, which would be a nucleon, such as a proton and neutron, and do collision experiments but the using of ball disk magnets didn't work, so perhaps disk magnets would work. We can look for a method to measure the speed of the magnetic force. Now, in the STOE, that would be the permanent magnet force, not the electromagnetic force. The STOE found that these 2 kinds of magnetic forces of Maxwell's equations are different. Now, one of them, the electromagnetic force, appears to be producing the electromagnetic waves which travel at the speed of light, and that is the speed of Hodge. Pisangro and others looked at the speed of a Coulomb force and found it to be many times the speed of light, and the STOE would suspect that the speed of the permanent magnetic force would be a plenum thing, and therefore would have a very high speed relative to the speed of light. The trouble is finding a way to measure that. Consciousness is something I think about for a while, but I think before the industry can go forward, it has to define just exactly what consciousness is. And that, of course, is lacking in today's discussions. STOE views life and societies as part of our universe. Therefore, the basic postulates of physics should also apply to life and societies. And I looked at that in this paper. But of course, the reverse is also true. That is to say, the characteristics of life should also apply in physics. That is to say, life expands by means of giving birth, and so there must be a form of birth in physics, which the STOE looks at. In the STOE, I looked at emergent characteristics, and these are a little different than what most people mean by emergence. But if we apply consciousness to the STOE, it could be an emergent characteristic, which means human and animal and plant emergent characteristics, or it could be present in all objects in the universe, such as rocks. Now, this has once been suggested by ancient Greek philosophers when they noted that objects, meaning rocks, tend to find their natural place in the universe. That means they have to know where their natural place is, and also in the view of where Hades is compared to heaven, meaning heaven is up and Hades is down into earth, because the earth was considered at the center of the universe, at the center, but not the center, because all earth is a gravitron. Oh, well, enough of that. Current approaches tend to view the brain as a digital computer for processing and collating information. Now, the STOE approach might be very different from that. It could view the brain as an analog mechanism. Therefore, it can have a great many more levels per given unit of time, which means a great many more digital processing rates. We could also, something I've been working on for quite a while, is to consider a third U.S. Constitution. Humanity seems to lack sufficient understanding to form a government with long-term survival. Most types of government organization that we know of have failed in the past, except maybe perhaps for the U.S. one, and yet that seems to be in trouble. The best that these organizations have done, such as the Roman Empire, is to transition from one form to another that collapses. That is to say, the nation collapses to a state, such as the Greek city-states, which then collapse to be tribes, etc. And I've written a couple of papers starting to examine this about steering humanity's growth and the growth challenge of the United States. Well, those are the things I'm thinking of for application of the STOE, but of course other possibilities are open also. Throughout this presentation, you will see an IA followed by 4 numbers. This is a link to the website, Intellectual Archive, and these 4 numbers reflect the paper that's on that link. The STOE has some predictions. A model should have predictions for it to be valid, at least explain problem observations while reducing to current successful models. So what we're going to cover here is going to be 5 predictions for sure, 2 that might be predictions, and 1 that seems to be developing over the last few years. Now, prediction means data ahead in time. So you make the prediction, then the observation verifies it. And a second thing is that all other models must fail. I mean, it's not a valid scientific theory if you hold a pen above a desk and you release the pen, that it drops to the desk. Many models suggest this, so that's not really a prediction in the STOE or any other model, because many models suggest this. Some consider a model describing existing data as prediction. I don't. And the prediction must be different from what other models predict and describe, as we said. The STOE model predictions started in 2006, and here's the archive reference about the Pioneer anomaly. These are the 3 predictions that the STOE had in its analysis of the Pioneer anomaly. The STOE predicted there was a Pioneer anomaly before the flyby encounters, whereas traditional models held that there was no early Pioneer anomaly, that is to say, before the Saturn encounter. The the other models had the Pioneer anomaly as being sun-directed. The STOE was the only model at the time, meaning 2005, 2006, was the only model to hold it was Earth-directed. The STOE held a decay in the Pioneer anomaly, whereas other models suggested only slight temporary decay around the planet encounters. I might also note that the STOE is the only model to describe all 10 of the Pioneer common characteristics that were pointed out by Anderson in 2001. However, these were known, and therefore describing them is not a prediction. Most other models of the Pioneer anomaly only talk about one or most two of the characteristics, and therefore they fall short. Also, the Pioneer anomaly paper mentioned trans-Neptunian orbits of Pluto, the TNO orbit of Pluto, caused by the galaxy source. Planet 9 data in around 2013 papers of TNO objects attributed their orbits to a, quote, planet 9, which is directly opposite to the sun from the Earth. Now, this should be reminiscent for the explanation of rotation curves being caused by dark matter, whereas the QSSC and the STOE model attributes it to the source of the stuff of our universe coming out from the center of galaxies, spiral galaxies, and they're caused by sources. The interference of light in the transparent mass experiment was predicted. Indeed, the experiment was constructed to use the effect to examine in the index of refraction in papers. The Hodge apparatus, a single slit with the second mass placed in the diffraction pattern, was used to examine interference effects of objects. The key is the diffraction variance of intensity from the slit in the second mask. The maybe prediction, I started by noticing Maxwell's equations differ from the STOE. The experiment that rejected the Biot-Savart law, there's the reference, was done because the EM radio signals travel at sea, which implies the Hodge are the elements. However, this seems to conflict with the Biot-Savart law. So the typical experiment was done using a magnet rather than a parallel wire, and the Biot-Savart law, as it's currently stated, was found to be incorrect, experimentally incorrect. The result of this experiment suggested the STOE another experiment on electromagnets. And this is the paper which showed two different types of magnetic field and that the Maxwell's equation should be done. The developing prediction comes from this paper about neighboring galaxies' influence on rotation curves. Recent studies from 2017 and on suggest correlation of spiral galaxies' tilt is related to neighboring galaxies.
Right. That seems to be the conclusion of that. So let's see. Can we get back to? I'll stop sharing my screen so we can engage more generally. Let me see. How do I do that? Let me see now. Stop. See now. Share screen. I'm not sure if I'm succeeding in cancelling it now. Screen sharing was cancelled. Yes, make sure that I've done it. Yes. Sorry. I beg your pardon for messing around. Okay. Well, there has been a tremendous amount of information in that. And I must confess that in the first minutes of the video, I thought for a moment we'd played the wrong video because we were specifically dealing with the Pioneer anomaly on the Planet 9. But John, of course, did deal with that in some detail later on, and he dealt with many, many other things. So I'm sure there are many, many questions. And again, as in the last session, dealing with the videos of John Hodge, I've been glued to the video and I haven't looked at all at the questions. So perhaps with your permission, I'll just quickly go through some of the questions, which may have been answered by John to a certain extent. So we'll have a look. Let's see now. Okay. Quest is asking very general questions. How does it work? Doesn't it? Especially yeah, it just reminds me of something. He's saying for many years I've thought it's possible there's multiple more planets within our solar system. I mean, it's a bit arbitrary. Pluto was considered a planet, possibly Planet 9. Now it's not. These things are a bit arbitrary. It sort of reminds me of the debate which people like the philosopher Hegel was involved in, where they were saying, well, there couldn't be more than 7 planets because 7 was a perfect number. It was like a divine number. But that could be answered. I think it was Jacob Bronowski who referred to the Shakespearean play King Lear, where the fool says to the king, the reason there are no more than 7 planets is a pretty reason, my lord. And the king says, why, yes, the reason is that there are not 8. And then the fool says, oh, king, you are quite right. That would make a perfect fool. So anyway, let's go on a little. Okay. So this questions opposing heat radiation talked about directly seems reasonably. A lot of these are just conversations going back and forth. So I'll not bring them up unless there's specific questions on John's presentation. Okay. So I think John answered one of Quest's points, saying the rotation velocity from one side versus the other side. Okay, let me just see now. We'll just dispose of these before getting into a more detailed conversation. Let's see. Quest asking, what is it that is rotating? And John just says hydrogen on stars. Let me see. This was the observation that I myself had made. Cornelis just said. I thought it was my fault. We played the wrong video. But in the latter part, John did get to deal with the Pioneer anomaly, which we know that we'll discuss in a moment. Okay. Trouble is, as I get through the questions, more and more are coming in. So let me see. What does John say here? STOE has one equation to explain all size scales. The video is applying the universal equation to galaxy and solar system scale problems. Okay. Question says, I read that the observation of the Pioneer anomaly suggests that Newtonian physics is seemingly shown as accurate. Perhaps I could just raise one point here, John, and perhaps I'll bring you up. You said that STOE rejects things like Lagrangian and Hamiltonian dynamics, but I mean, surely the dynamics developed classically uh, are based on an idealization. So you can bring in friction and dissipation and the second law of thermodynamics and so on, but that doesn't mean that the dynamics per se are incorrect. What would you say about that? Your statement that there's a conflict.
Well, those developments that occurred in the late 1800s primarily focused on energy, and that's what the Lagrangian and the Hamiltonian are. They're equations involving energy. Whereas what the STOE is doing is it's talking about only forces as being the first abstraction from observation. So you observe something falling, its position and how fast it's changing position. And then you calculate a force. That's Newton. But when you go to energy, that's where things start getting lost. As you mentioned a couple of them, that's, friction, for example. Generally in applications, you tend to ignore friction. But the redshift model is essentially a friction model, meaning as a photon is traveling through space, it loses Hodge, and that's a friction kind of action, you see. So it rejects the, okay, please.
Well, maybe related to that a bit, John, Quest has asked, but I think you've answered it. Just to inform the participants, is it somehow heat and energy which causes the pioneer anomaly? And then I think you've said...
that's the standard model.
10 characters of the PA. Popular physics uses thermal cause to explain only one, leaving the remaining 9 unexplained. What are all those other 9 characteristics?
There was a couple associated with. Well, I guess there isn't really a general. There's a couple that are associated with the programs used. There's others associated with the sun. That is, there's a periodicity noticed relative to annual periodicity and diurnal periodicity. Let me see, what were some of the others? Yeah, that's it. And then, of course, there's other anomalies associated with flybys being very close to a planet. And that's where the standard physics just loses
it. You also made a point that you were going through all the anomalies, which holds right. Acceleration is not real.
Right. One of the characteristics that Anderson noted was that one of the Pioneer spacecraft appears to have a slightly lower anomaly than the other. And the STOE ascribes that to be because that spacecraft is heading towards or nearly towards the center, which is a source in the STOE, right? And the source is putting out a force outward. That's what causes the rotation curves, as well as Planet 9. You see, so the presence of the source in the STOE means there's another force in our solar system that's acting outward from the source, you see. So that's going to cause quite a few anomalies noted in the solar system, just that I haven't gotten around to the others yet.
Okay, well, maybe that to a certain extent answers Cornelis's point. He says obviously one should be enough to explain the velocity.
Well, that's the interesting point, is that the spacecraft is behaving more or less according to Newtonian physics, or post-parameterized Newtonian physics, PPN, which is generally Newtonian physics type application to spacecraft. Now, there is a question of whether or not that change in position, meaning velocity, is real. Back around 2006, that was a big question in the various study groups of the Pioneer Anomaly, was questioning whether or not this apparent acceleration was real, or whether it was a signal effect, you see. Now, the STOE says it's a signal effect, which means the acceleration, that is to say the spacecraft is really where we think it is, and not someplace else. So that acceleration is not real. Now, in the 2006 time zone, they were putting together a Horizon spacecraft program, which was going to go out to Pluto. And part of that program was to test the standard model, which is the thermal explanation. That is that the position of the spacecraft is really closer in, than it was supposed to be. And they were going to do that by simply turning off the spacecraft for an extended period of time in where the Pioneer Anomaly was experiencing this, and then turn it back on and see where the thing was. Well, they launched it in 2009, 2010. Now, this was after the thermal analysis became firm and accepted, and they deleted that part of the program, which is really a shame, because the other nine problems of the Pioneer Anomaly essentially begs for new physics, such as the STOE. But of course, as far as I know, there's no one that's come up with any kind of model that, when applied, could yield the other nine. Now, here on Stephen Gift, Stephen Gift was part of a team that looked at the solar periodicity, but I don't think he got it right. But that might be something that Stephen might talk about. But anyway.
Okay. Well. Perhaps we'll leave the questions there for the moment. We can always come back if there are any pressing further statements. And if anybody has any contribution in the green room, he can come up. However, I might bring James Keane up first, if I may, because he's made a number of points here in the private chat, which I can't actually put up on the screen. And one has been answered by John. Basically, if I may read out, is there a correlation between distance and galaxy type? Jim asks. And then John says, no, and that is a current problem. Why do very different distant old galaxies look like close galaxies? So there's no major difference, you say. So if I may, Jim, if you just have anything more in respect of the points you've raised already, which are interesting, or you can maybe...
Well, thank you. I tried to Google STOE theory, and it doesn't come up on Google. Also, the President John Hodge that we now see, John Hodge does not come up on Google either. Another John Hodge comes up. Is there a link defining the STOE theory?
Well, almost all my papers are on RG.
RG, what is that?
ResearchGate.
ResearchGate?
Yeah.
ResearchGate.
Yeah.
I thought you had your own website. No, John.
Well, yeah, I used to, but I kind of let that lapse. I mean, I'm putting papers up on ResearchGate and
Okay.
something called the Intellectual Archive.
Research.
Intellectual Archive.
And by the way, I'm delighted. I didn't put up the link, the direct link for today's chat. It appears I don't need to now because any problems, certainly that you had, Jim, seem to be resolved. You could get in directly from the global link, which was given out in the announcement. I was a little worried about that, but it seems to be working now. So, do you want to raise anything else, Jim, while you're up?
Yeah, well, unfortunately, I'm a little bit at a disadvantage because I don't want to be impolite, since I really need to review the STOE theory first before I can have maybe intelligent questions. Last point is I might point out that my lunar laser ranging paper also concerning the effect of surface temperature on gravitational phenomena also might pertain to the Pioneer anomaly, and I don't know whether Mr. Hodge is familiar with that work on what I call the law of motion in binary mechanics. I suppose he's not. So you might want to put that in your notebook to take a look at that.
Well, I looked at binary mechanics years ago.
Oh, you have looked at it?
Some years ago. I haven't looked at it more recently. But I'm
Well,
not
I
familiar
think
with
my lunar laser ranging paper showing motion of the moon with respect to Earth based upon surface temperature of the moon surface facing Earth was, I think, in 2011. And it mentioned the same thing, the importance of temperature and sources of radiation in the Pioneer anomaly as well. So anyway, thank you very, very much.
Okay, well, thanks for that reference. And John and any of the rest of us might be well advised to have a look at that and perhaps come back to you. So thank you very much, Jim. Before asking for any other contributions from the green room, may I just ask a very general question? You say in your summary that you don't, or STOE doesn't concur with the Big Bang theory, which is not surprising to us, perhaps. But do you have any general view as to how the universe began, or indeed did it have a beginning? What's your cosmological or cosmological view about reality?
You're talking about whatever is the creation myth.
I suppose so, yes.
Yeah. The STOE doesn't, I don't say anything about that because simply I don't know. And neither does anybody else, But I'm not too sure why people want a creation myth, but the best we get to with, see what the STOE does, it starts from what we know, and then it tries, which are experiment and observations, not theories, experiment and observation. And then it tries to figure out what is the model that explains all of what we can know, meaning what our experiments and observations are. And we don't observe the beginning of the universe. We observe far out. We presume that that's closer to the beginning, but when it gets to actually where we, meaning our galaxy, came from, I'm not too sure that the universe isn't but much more than 100 billion years old. Meaning, what I visualize, I once wrote a paper on that years and years ago, maybe 25 plus years ago, is that like Halton Arp, you have one source created. And as you notice with the STOE, one source eventually creates others, which are called QSOs, and in Harp's analysis, from one source you get one spiral galaxy, and from that spiral galaxy you get QSOs being ejected, which are turn into other galaxies, other spiral galaxies. As all this matter gets ejected from spiral galaxies, you eventually form elliptical galaxies, which then, well, they form the galaxy clusters. But this could have been going on for a long time, and thus creating all these other galaxy groups that we see. I mean, that's the closest I get to from beginning.
So basically, there's nothing in your model which would contradict the possibility that the universe was created at some time, or indeed, there's nothing in your model that would contradict the contention that it always has existed and there was no creation per se. Is that fair?
Oh no, no. The idea is that the stuff of our universe is created and is still being created at the center of spiral galaxies. Then this stuff goes out to elliptical galaxies where it is annihilated from our universe. So,
but that's like a continuous creation, equivalent to maybe the ideas of Fred Hoyle many years ago. It doesn't necessarily mean that that nothing existed at one time.
I would like to think that at one time nothing did exist.
Okay.
The analogy I wrote here, and here you get kind of philosophical, and you start waving hands a lot. But everything we know has a beginning. We are born, we have a beginning, and before our birth, we were what? Two gametes, And the same holds true for everything. Everything in our universe has a beginning. Also, everything in our universe that we know of has an end. So why shouldn't the universe as a whole have a beginning and an end? But I don't accept the idea that the beginning was all of a sudden there was everything in the universe at one point, that they'd expanded. Matter and stuff is continually coming. The Big Bang idea simply does not explain all of these observations. There are many, many observations that the model does not explain. Several of them have been added to with ad hoc kind of things like dark matter and dark energy. Others, like, well, we covered one today, the asymmetry of the rotation curves. At one time, that was a very popular topic. But they couldn't find a reason. They couldn't find a formula to describe asymmetry of rotation curves. And so it was just kind of dropped. But it's still there as an observation that is unexplained. And of course, nine of them.
Yeah, well, thank you for those very specific points, and also for the more philosophical ones. I mean, you raised quite a number of very interesting avenues for future research in the latter part of your presentation or of the video, relating to things like social elements and formation of societies and evolution and that sort of thing. But I'd like to see, is anybody else in the green room like to come in at this stage, or shall I volunteer? Harry, I think, does. Yeah. Sorry, it took a time to get to you, Harry, because you're at the bottom of the screen here. But I'm going to bring Harry Ricker up now. So what's your response, or what's your question, Harry, about all this?
My first well, I have a whole bunch of questions, but anyway, I have two issues. One is the rotation curves, and the other issue is Maxwell's equations are wrong, which I find a little bit hard to accept. On the rotation curves, you took a selection, sounds like you took 118 galaxies, is that correct? And then you
the number, but it's something like that.
So you analyzed 118 galaxies. Now my question is, are they all the same type? Are they all SAs? Are they SBs or SCs or whatever? Are they all the same type of galaxy, or are they all mixed up as far as being different types of galaxies?
All the 6 Hubble diagram type galaxies were represented in the sample.
So in other words, this whole business of rotation curves and differences in the curves could be completely attributed to the fact that they've got different galaxies included in their sample. And so different galaxies, you're comparing apples and oranges. You're not even talking about the same thing. They're completely different galaxies.
I'm not too sure where you're going with this. All the different galaxy morphologies.
Well, I mean, an SA galaxy is not the same. An SA spiral galaxy is not the same as an SC spiral galaxy. You know about this terminology? There's SA, SB, SC. It's in the Hubble diagram. Then you have SB, SBA, SB, BS, different types of barred spiral galaxies. So you got barred spiral galaxies and spiral galaxies all mixed up in the same group, right?
That's correct. But
so I'm not really sure how you can make conclusions out of that, frankly, to be honest with you.
Well, what you got is data.
Yeah, but okay. So if I have a barred spiral galaxy, that's a galaxy which has a bright bar that comes out of the nucleus, and it's an asymmetrical form galaxy. In other words, the form of the galaxy is asymmetrical to begin with. So if you were to measure the rotation curve along the bar, okay, I would expect you get one result. If you measured it 90 degrees away or 180 degrees different from the bar, you didn't measure it across the bar, then you get an asymmetric result because there's an asymmetric form in the galaxy to begin with, right?
The definition of a rotation curve is along the major axis from our viewpoint.
Okay, so how are you going to establish what the major axis is? That's a definitional problem, it seems to me.
What? I don't understand. The major axis is the longest axis from our viewpoint.
Yeah, but that's only really determinable for a particular type of galaxy, whether it's an SA or an SB or an SC, or is that true for a barred spiral galaxy or not? What type of galaxy are we talking about? I mean, there's all these different forms, and the problem, as far as I'm concerned, is unless you're comparing the same form of galaxy, what have you accomplished?
The procedure here was to look at rotation curves and then find out why they have given values. To apply the universal equation, the STOE universal equation, you have to look at luminosities, which is what I did in the graphs. Now, any one of those lines that I show, of the 6 lines, will have different types of galaxies on it.
Well, my problem is that when you showed the chart, when you showed the chart, it didn't say on the chart what the form of the galaxy was, whether it's an SA or an SB or an SC or what is the Hubble classification of the galaxy that you show on the chart? You don't show that. So I don't know whether you're comparing apples and oranges. Huh?
The chart is merely the summary. If you look at the paper that was quoted, you'll find that there's a table in there that lists all the galaxies, and that includes their morphology.
All right. Well, you didn't show that in your tables. Anyway, I'm
Well,
sort of mystified by this whole issue. I don't see how you can draw conclusions unless you're comparing the same morphological galaxies. In other words, I don't understand. So if you've got a different morphological galaxy and you get a different rotation curve, well, that doesn't surprise me because they're not the same thing. So I'm not sure where you can draw conclusions out of that. Okay.
I guess I have two views. One is they fit the equation. I was able to find an equation that fit all those galaxies, including all the different morphologies. I mean, you saw that. Now, the reason why you get those 6 lines instead of just being one line, I went into about the data. That is to say, generally people, standard science, will look at one line, they'll accept a very high error rate, meaning 30 to 40% error, and then they'll draw one line and forget about 20% of the galaxies, ones that are really off the graph. As that's what we did in the paper. But I accept all the galaxies, and then I want to fit an equation to them. Now, the subtlety here is, I think, is that this business that you can do exactly what you're saying you shouldn't be able to do, which is exactly what I did, indicates there's something fundamental about these things. And I don't know what that is, right? I just found something that is very fundamental. It fits the universal equation, and it has these 6 different lines. Why, to me right now, is a matter of speculation. But it works.
Well, I don't know. I don't know if this complicates matters or maybe resolves it a bit. But I sometimes raise this, that I view what we see as a galaxy at any particular time as being a composite image, because any point in the galaxy that we see, it must be the same distance in light years from us as the number of years previous to the present that it emitted that particular light which we're seeing now. So you could have a galaxy which is rotating, for example, and you might be seeing different parts, or indeed even the same part at different times, and it appears maybe to be spiraling out or something like that, whereas perhaps it's merely a globular structure which is moving. Now, I don't know what you think about that idea, but I mean, if that idea has some merit in it, I don't know if that helps your idea that you just looked at all these different, apparently different galaxies and got the same sort of relation for the rotation curves. Would you have any comment on that, John? Good, bad, and different.
Yeah. I don't know. The view of a galaxy is, as we see it, is as a cohesive, gravitationally bound bunch of stars and other matter, hydrogen, asteroids, etc. Now.
Okay, let's move on to my second issue, which is why are you saying Maxwell's equations are wrong? Not clear to me.
Because we did some experiments, not in this video, but in what was it, the February video? I mean, the first video that was presented here in CNPS was about that. And we found things that are incorrect. One is that the divergence of the magnetic field is not zero. The magnetic field is asymmetric. See, so everything you want to do, del B is not equal to zero all the time. If it has a Hodge in that Gaussian space you construct, that will not be zero in that Gaussian surface. The other has to do with back in Ampere's day. One of the assumptions that Ampere put into his work was that any given element along a wire radiated whatever that force was in all directions, and that was shown to be incorrect by experiment, where I used a wire and a magnet beneath it and showed that the current just above the magnet is the only thing that influenced the force on that magnet. So,
well, that's not exactly Maxwell's equations. That's an Ampere's law, which is a different issue in my view. The Maxwell equations does assert that the source of the magnetic field, that sources don't exist in the magnetic field. So del dot B is zero, so which is saying there are no sources of the magnetic field, such as monopoles. And so you kind of, I would agree with you there on the Ampere's law thing. That's not really in Maxwell's equations explicitly. I'm not sure exactly how that interprets. The issue in my mind is that people have different interpretations of Maxwell's equations and interpret them differently. Whereas the physics people, they give you these equations on a piece of paper and tell you that's everything that you need to know about electrodynamics. But it turns out, electromagnetism, turns out you need to know more than just those 6 equations to really understand what you're talking about.
Back in my engineering days.
People have different interpretations of what Maxwell's equations means. That's my whole point. And
yeah, well, I agree.
So I'm not sure whether you're interpreting them differently or.
I mean, the way I look at it, for what it's worth, is that they're not incorrect. That they're just perhaps not totally general. So, for example, they lead to a radiation type which is transverse and which moves with this very specific speed, and that is one type. But there's another type of radiation which is like a scalar type, again to use the same term as you're using in your theory, which maybe doesn't directly come out of Maxwell's equations. So I say that they can be generalized, but I don't say they're incorrect. It's just maybe another way of looking at things.
Well, I want to get down to there are 2 types of magnetic field. That kind of was an explicit statement. So could you clarify what you mean by that?
2 different types of magnetic field.
Did you say that earlier?
Didn't he say that?
Well, there's a North Pole and a South Pole.
Yeah.
Right? I mean, you have a North Pole and a South Pole.
It wasn't merely that, was it?
No. Well,
okay. Well, I guess I missed that. If you could clarify what you meant by that. Do you agree that this was something that was mentioned, right, Ian? Did I hear that correctly?
As well, Harry, but I can't remember exactly the context. I'd have to go back over the video.
Well, that kind of got my attention, to be honest with you.
Yeah, in the STOE, I hold that there are North and South poles. There are no unipoles, right? So where there's a North Pole, there's a South Pole. But the strength of the North Pole and the strength of the South Pole to repel is different, which means the polar strength is asymmetric. Now, in the end, the smallest piece of matter is the Hodge, and what the Hodge is a magnet. right? I mean, it's the north-south pole on one side, north pole on one side, south pole on the other. And it's these magnets that then attract and form particles and stuff. That's where the one force comes from. There's one force. So you don't need strong and weak nuclear forces because those things, those particles, are magnets. And that's why the protons are held together, because they're magnets. Right? And the magnetic field is asymmetric. So when you take and you draw a Gaussian surface around a Hodge or any matter, you'll find that there is a net force because of the asymmetry. Del B is not equal to zero.
This isn't the point that we thought you were talking about, Robert Kay. He said he mentioned in the video that there is a difference between electromagnetism and permanent magnetism.
That's correct.
So maybe that's the basis to Harry's question.
The measurement different. And again, we're going back to the first video back in February or so. What the experiment was, I'm measuring the repelling force of North Pole to North Pole and South Pole to South Pole with permanent magnets. And I see an asymmetry. One pole is stronger than the other. I do the same thing with electromagnets, and what I see is both poles are the same. You see, so permanent magnets have an asymmetry, electromagnets do not.
So are you saying that if for the case of electromagnetism, the divergence of B does equal zero, but in the other case, it doesn't because of the lack of symmetry?
Yeah. That's the first approximation. that del B equals zero for electromagnets, where the Gaussian surface includes the whole electromagnet. But
so that's
what electromagnet?
You're saying.
What electromagnet is the other experiment I explored there, where you take a wire, and you notice an electromagnet is nothing but a coil of wires. So you take a wire and you explore what the magnetic field is there by putting a magnet, and you measure the force on that magnet from the wire, varying with current. And what you find is that the Ampere's assumption does not hold, meaning it's only over the magnet, perpendicular distance. What's happening in the STOE, and that's a bunch of experiments I was hoping to do here before I died. What's happening in the STOE is that as electrons move across on the surface or in the wire, they're emitting Hodge. And what an electromagnetic signal is Hodge, a bunch of Hodge. It's not a magnetic field. It's Hodge, and the Hodge carry the magnetic field with them. Now, the way you see this is Hodge and photons and matter have a maximum speed limit of the speed of light. That's the speed of Hodge. But the speed of a Coulomb force can be millions of times faster than the speed of light. I mean, that's also experiment.
Okay, well, I think maybe Vladimir has signaled. Anything else, Harry, before we go to?
Well, I just want to remind people that we're going to have a cosmology meeting tomorrow at 10. So anybody, just remind people.
Yeah, what's the link on that? What's the link on that?
Send me an email and I'll send it to you.
What's your email address?
kc3mx@yahoo.com.
KC3mx at yahoo.com.
KCMX.
KC3MX at yahoo.com.
KC3MX. And I think there'll be 3 links because they last about 40 minutes or half an hour. Okay. Okay, well, thanks very much, Harry. And we hope to see you there, John. I'm trying to go to it myself, although it's a bit difficult to go every week, but I'm trying to rearrange tomorrow afternoon so I can go there. So
Is that the same time as this one?
it
10
is.
o'clock.
Yeah, it is.
It starts at the same time. 10 o'clock New York time, Eastern Daylight Time.
Okay.
On a Sunday, tomorrow. Yeah. Okay. Well, thanks very much, Harry. I'll bring you down for the moment now. And I think we had Vladimir first, who just wanted to come. So, Vladimir, you're up now. Very welcome.
Okay, thank you so much for detailed analysis of some experimental results. I'm very impressed. I didn't know most of them, but I absolutely agree with 2 comments of Harry. First of all rotation curves depends on morphology of galaxies, no doubts about it. A few years ago, Lee Ludwig, there is such a scientist, he showed that for rotation curves, we don't need anything, dark matter or other explanation. We must follow only gravitomagnetism, and instead of gravitational forces, to calculate gravitomagnetic forces that in conjunction with mass currents. And he explained our galaxy such a way and simple like this. What does it mean? You have your rotation curve depends on the movable masses inside of the galaxies and the multi-body mechanics. You must use your computers. You cannot imagine how they influence on each other. That's why, morphology, this is the most important part for rotation curves, because rotation curves is the result of movement of all the masses inside of the galaxy. I absolutely agree with it. I talked in my presentation about this, and there is no doubt for different morphologies, different galaxies will be different rotation curves. And rotation curves is internal business for each galaxy separate. The next question is about Maxwell equations. I absolutely agree. Don't touch Maxwell equations. There are no forces in Maxwell equations. There are only energy density, charge density, fluxes of energy density. That's it. That's it. Nothing else. All the rest. By the way, I want to ask you the question. What does it mean force in your definitions? You told there are some different forces. I don't know what does it mean force. Tell me, what does it mean force?
The force in the STOE is the gradient of the plenum density.
Of
And the
what?
plenum density.
Of what density? Of energy density, mass density, or what?
No, plenum density. And the plenum density is the universal equation.
Okay, because I don't know what does it mean force, because I know a little bit in our macroscopic physics. My main question is, please, Maxwell equations is a classical equations. You cannot apply them to micro objects. Quantum physics, don't touch it, because it's valid only for macroscopic phenomena. That's it. I don't like when we are trying to put our Maxwell equations inside of electrons or atoms or whatever. That's why, I don't believe that it's possible to create any theory for quantum objects and macroscopic phenomena at the same time, because macroscopic phenomena, they have totally different laws, totally different physics, because it's based on ensembles of micro objects. That's why, it's two different stories. That's why, all physicists right now, they've done some mixture between Maxwell equations and micro objects, quantum physics, and all this stuff. Let's stop talking about this. Let's use the definitions and the physics, classic physics for classical phenomena. Quantum physics, we don't know anything about it because there are in quantum objects, there are no space, there are no size, there is no time, there is nothing. I don't know what does it mean quantum physics. Do you know what in your case quantum physics? What do you mean?
If I may just add, if I understand it, Vladimir, like physicists have been singularly unsuccessful in integrating the two. Are you suggesting that they should divide the two into two different areas?
Yes,
different arenas?
totally different. As I told many times, very good example. We have our air outside. We have molecules flying in here and have some, connections. They push them to each other and so on and so on. And we have a temperature. What does it mean, temperature? Temperature, it's an average kinetic energy for all these molecules. Energy, energy, kinetic energy for ensemble of them. Then each particle flying around us, they don't know anything about temperature. And temperature knows nothing about each particle. It knows only average kinetic energy. How you can compare one to one? How? This is exactly my point. We must stop some border between classical and quantum physics. Let me tell you this border. I told the minimum size for classical physics is 10 to the minus 14 meters. That's it. And it's calculated by myself based on classical experiments of 19th century, before quantum physics, before this relativity and all this stuff. There is no space and time before you have the medium of the world. You cannot do it. For quantum objects, there is no space, there is no time. I don't know what does it mean. I don't know what does it mean, Schrödinger equations and all this stuff. I don't know.
So, John, do you think that's a fruitful approach to separate the macro from the micro and to deal with them basically in a non-integrated way, as Vladimir seems to be suggesting?
The quest of physics, period, is the quest to come up with a single theory to cover everything in the universe. The theory of everything.
So you're endeavoring to do the opposite.
To do just that. So I want one equation, my universal equation, with one force, not electromagnetic, not weak, not strong, one force to cover the small. And I demonstrate that with the double slit experiment and the transparent mask experiment, okay, and cosmology. So I had cosmology last time, and this time we got solar system and galaxy scale observations.
Well,
So
might I suggest that this very interesting topic might be reverted to perhaps after the next lecture, with your permission, Vladimir, because we're running out of time, and Denny has asked for the floor, so I'd like to give him the opportunity. So perhaps we could come back to it. Very good point that you've raised.
And I want to, maybe if we'll have 1 minute time, I want to talk about the Pioneer anomaly. Okay, please go to Denny. Because
Okay,
Pioneer
anomaly.
Okay.
Okay, thanks. Denny, you asked for the floor.
Yes, you say the law of Biot and Scalar is incorrect experimentally. Can you give me a reference to that?
I could, not right offhand.
Well, let me give you my email address. Allen's, A-L-L-E-N-S.
Just a minute.
A-L-E-N.
A-L-L.
A-L-E-E-N.
Two L's.
Yeah, A-double-L-E-N.
A-double-L-E-N-S 10 at sbcglobal.net.
sbcglobal.net.
SPC.
SBC.
BC. S is in Sam, B is in boy, C is in cat, global.net.
Because when this was mentioned, Denny, by John, I was thinking that Wesley, J.P. Wesley, claims that the Biot-Savart law is not generally true because it doesn't conserve energy. Or another way to look at it is it doesn't afford a demonstration of Newton's third law. It isn't reciprocal. So he brings in more general ones.
Yes.
Yeah. Okay, but it'd be interesting to see what John says on that. So if that's all, we might be able to go back to Vladimir very quickly to get his point on the Pioneer.
John, did you get my email address?
Did you get the email address, John?
ALLEN as in November.
November.
S 10.
Samuel, 10.
Yeah, 1010.
At
SBC global.net.
.net. Okay. Oh, okay. Thank you. And we'd like to hear more about how you get on with that. So if that's all right, Denny, I'll bring it down. And Vladimir, you're back, but please be quick because we're running out of time.
Yes, I will try to be quick. Pioneer anomaly. You know, there is such a halo around our sun. Do you know about the solar corona? When we were observing solar corona, we can see this X-rays at the diameter of solar corona 10 times more than the diameter of sun itself. What does it mean? We have a matter around. Matter has a mass. It should be some additional gravitational force. It is exactly one of the points for explaining Pioneer anomaly. I calculated this halo around sun, and I showed that this acceleration for this Pioneer, it's exactly can be explained by this halo. The second very important point is, one more time, gravitomagnetism. These Pioneer bodies, they're moving around all these masses. It has not only mass and gravitational force, but it has a huge gravitational mass current. And you must see what the influence not only of masses, sun, earth, and this body, I mean satellite, but gravitational mass currents. And then, only then, you can explain in details what's going on with them. What is my point is right now, we are in business of multi-body mechanics with two kind of forces, like, gravitational and gravitomagnetic forces. It's a very complicated, issue, very complicated task. We must put all the computers to calculate it, and only then we can make a conclusion. What does it mean? Thank you so much.
So maybe, John, a very brief response. You may wish to go into more detail later with Vladimir on it, but very brief response to the point he's raised there.
It sounds like, and correct me if I'm wrong, it sounds like he's accepting that the Pioneer anomaly is indeed an acceleration of the spacecraft. I mean,
which you deny.
The STOE does not accept it. And the STOE says it's a radio signal effect only. The spacecraft is not being influenced by anything outside of the PPN type forces.
Well, would you forgive me if I asked you to terminate the conversation now? It's very, very interesting, and there's no problem in having a disagreement. In fact, that's a good point. It means that we're thinking independently. But Vladimir, we might come back to this very important point that you've raised. So if I may just bring you down, and we'll talk again about it. Thank you very, very much. And so, John, as usual, it'll devolve upon me to close the meeting just in about a minute's time or so. Anything else you'd like to say before I do that?
Well, thanks for the time.
Well, that was succinct, and thank you very much. So, and it's my pleasant duty just to emphasize that we're very delighted actually that we've had the opportunity of showing these videos, two so far. We're hoping to show the third and final one of this series next time in 2 weeks' time. And indeed, having John here to help us through the videos, and he's been very tolerant with our questions, and he's answered things, in real time when the videos were being played, and he's also dealt with questions which actually would really take a long time to go into in more detail. But that's a very, very good sign. It indicates that he stimulated us in our minds, and we've all looked at our own ideas and our own theories, and we've seen how they may be complementary to John's ideas, or they may contradict John's ideas, and there's nothing wrong with that at all. It means that we're all independent thinkers and we're not just following one line. And I think a number of things have been raised which with benefit we'll come back to. So I'm looking forward to the last and final session of this series of videos, and I'd like to thank all of you for your contributions. I have looked, I think, at almost every question that's come in. Unfortunately, I haven't been able to deal with it because that would take a long time, and there were more of the nature of conversation between people rather than questions. I did deal with the ones which were specifically questions. But thank you very much for your contribution. We look forward to your continuing contribution. And as always, thank you very much, people in the green room. I see Cornelis has joined, and unfortunately we haven't had an opportunity talking to him, but we'll do that perhaps next time. So thank you all very much, and we look forward to your continuing contributions in regard to John's next lecture, which will be in a fortnight's time. So I'll wish you all a very good day.